Application of Laplace transformations in electrical circuit analysis. Consider RL series circuit as shown in the figure, with imposed voltage being V of t, circulating current being I of t, at any finite value of t after switching. Now, applying Kirchhoff's laws, you will be getting R I of t plus L d I of t by dt equals to V of t. As we know, the Laplace transform of f of t equals to capital F of s, and Laplace transform of d by dt of f of t equals to s f of s minus f of 0 plus, and Laplace transform of integral f of t dt equals to f of s divided by s plus f of 0 divided by s. Now, by using these three fundamenta, Laplace transformation, now applying the Laplace transformations for this equation, we'll be getting R of I of t. So this is in this form. So capital I of s plus L of the second term is in differential form. So s of I of s minus small I at 0 initial value, which equals to capital V of s. So this is the Laplace transformation equation for the Kirchhoff's voltage equation. For this, if I draw a circuit, this is the resistance R plus an inductor less and connected to Li of 0 plus. So here plus minus, here it is plus, this is minus, then this is minus and plus here. So, and it is connected to a voltage source capital V of S plus and minus, and the current flowing through it is capital I of S. This is the RL circuit in s-domain. The initial current appears in the circuit shown in s-domain as a voltage source Li of 0 plus, and Kirchhoff's voltage law remains valid in s-domain also. Here I am giving a transformation of some conventional time domain to a frequency domain, sources and circuits. The first one, constant voltage source V. Sometimes we can take this as DC source. In s-domain, it can be represented with V by S. Time dependent voltage source V of t, s-domain as V of S. Constant current source I in s-domain, I by S, and the time dependent current source I of t in s-domain, I of S. Resistance capital R in s-domain, it's an R. Now, voltage drop V is equal to R IT in s-domain, V of S equals to R I of S. And sixth one, inductance element L in s-domain, it's S L, and the voltage given V of t equals to L d it by dt with initial current of I 0 plus is given in s-domain as V of S equals to S into L I of S minus L I at 0, and the circuit SL I of S flowing, so positive negative and negative positive L I0. Current in the inductor is given by I of t equals to 1 by L integral 0 to t V of t dt plus initial current I naught. This is in s-domain, will give us I of s equals to 1 by L V of s divided by s plus I naught divided by s from integral formula. In circuit form, I of s and the voltage between these two is V of s. Or simply we can write this as IL of s plus I naught of s, where I naught of s equals to this and IL of s is equal to this. Seventh one, capacitor. C in s-domain, it is 1 by Cs. Voltage V of t to the capacitor is given by initial voltage plus 1 by C integral 0 to t I of t dt. This in s-domain is going to give us V of s equals to V naught by s plus 1 by C I of s divided by s. equals to V naught by S, I of S divided by Cs. Now this we can represent with I of S goes to capacitor plus or minus. This is 1 by Cs, and the initial voltage plus and minus. This is given by V naught by S. If the initial voltage is minus V naught, then V of S is equals to I of S by Cs minus V naught by S. 1 by Cs minus plus V naught by S. Current in the capacitor is given by I of t equals to C dV t by dt. This in S domain will give us I of S equals to C of S into V of S minus initial voltage V naught. This comes from the differential form of the Laplace transformation, and it is represented in the circuit, and this is Vs plus and minus. 81. Mutual inductance. M. Mutual inductance between the two coils being M, the currents for each coil is I1 and I2, self-inductance L1 and L2, and the voltage drop in each link of the coil is given by V1 of t equals to L1 d I1 of t divided by dt plus M d I2 of t divided by dt. This in S domain will give us V1 of S equals to, in differential form, so L1 of S of I1 of S minus I at 0 plus M of S I2 of S, and this is I1 at 0, this is I2 at 0. In the circuit it can be represented as L1S, this is L1 I1 at 0, gives us I1 of S plus and minus, and this value equal to the second term M of S I2 of S minus I2 at 0. Next, similarly, V2 of t equals to L2 d I2 of t divided by dt plus M of d I1 of t divided by dt. This is in S domain, that is V2 of S equals to L2 S I2 of S minus I2 at 0 plus M of S I1 of S minus I1 at 0. Then this in circuit we can show this as, this is L2 S plus and minus connected to minus and plus of L2 I2 at 0 plus giving I2 of S, and given to plus and minus of M of S I1 of S I1 at 0. This is regarding the transformation of the source and circuits from the time domain to the frequency domain. Given a series RLC circuit with time dependent voltage and circulating currents. Now, applying the KVL, we are going to get V of t equals to R I of t plus L d I of t divided by dt plus 1 by C integral I of dt. This is in terms of time domain. Let us transfer this into the S domain. Then V of S equals to R I of S plus L into S I of S minus I at 0 plus 1 by C of I of S divided by S plus V naught by S is the initial voltage of the capacitor. Now V of S equals to R I of S plus LS I of S plus 1 by Cs I of S plus here V naught by S, V naught is equals to the charge divided by the capacitance C. So Q by Cs minus I0 naught. The I of S is given by V of S minus Q by Cs plus I at 0 divided by R plus Ls plus 1 by Cs. And here the Z of S is the impedance given in S domain. R plus Ls plus 1 by Cs is known as operational impedance. Now, from this equation, you can draw the circuit in S domain. This is RLC circuit in S domain. If this video is useful, please like, share and subscribe.